trying to prove whether this argument is valid or not, valid or invalid, not true or false, valid or invalid. And the way to do that is to take these originals, the premises, and connect them with an and then see if all of those, this and this, implies the conclusion. If our truth table ends up with this statement being a tautology, all true, then it's a valid statement. If it's not all true, then it's an invalid conclusion. So let's try. Now, we don't have P's and Q's, so that kind of makes me feel a little bit sad, but N and O's ought to work the same way. We have two statements, so we're going to need our normal setup. And then we need the promise. And the way that can be broken is with a true and a false. So there's our false. The rest are true. And then we need to do the or statement. So let's write that down. Actually, it's an and statement. I must have mispronounced the word and, called it or. So we're looking at this and this with or, and the only way that can be false is if both are false. Here, both are false, and so we have the rest of them being true. If there's a little bit of truth in an or statement, then it's true. And here now we have kind of the big conclusion. This is a promise, so the way it can be broken is if the first to the left of the implication arrow is true and to the right is false. And so we're using this and we're using this in that order. And so we're looking for a true false, and the true false is right here. So those are broken promises, and really we're done at that point. These would be true. But this is not a tautology. It is not all true. Therefore, this is an invalid argument. This is the way I think you should do these problems in our course, because we're a survey course and we're not getting into this very deeply. The book offers you another way of doing some of these problems, and that is to look at the format of the argument here and compare it to the known formats on page 140. And this compares to the format under invalid arguments called fallacy of the converse. Fallacy of the converse using P's and Q's looks like this. And can you see that this and this are exactly the same, just slightly different letters, but the same types of letters in the same place? It's the same argument. So it's an invalid argument because of the chart on page 140. There's several problems with doing it this way. The main problem is you'd have to memorize that chart and really understand it to use it on an exam, whereas we've spent a lot of time on truth tables, and you kind of understand how truth tables work. This is the heart of the matter. Using these from the table on page 140 is a matter of just memorizing a bunch of stuff. If we were going to do these arguments for a long time in a semester course, yeah, memorizing these would be a good idea, but I don't think so. So what I would encourage you to do is do the truth table, but then just notice those standard arguments. I think that would be the best of both worlds. So we're asked to check the validity of this argument. Is it valid that if this is true and this is true, that both of those two things imply that this has to be true? So we have the first one and the second one, and that has to imply that this is true. When? Always. So in the truth table, we're looking to see if this is always true. If it is, this whole argument is a valid argument. If it's not, then the whole argument is invalid or not valid. And so we need a table, and so I'm going to make that table. So we need a P implies Q, if and only if. It's a biconditional, and we know that this is true when both P and Q are alike. So it's true here, it's true here, it's false here, false here, false here, false here, true here, true here. And then we need, let me just double check. Yeah, Q implies R. And we know that this is false when Q is true and R is false, because that's the broken promise. And we have that here, and we have it here, and I don't see it anywhere else. And then it looks like we need an AND connecting those two. So we're doing an AND on these two, and an AND is only true when both of them are true. And then it looks like we need a negation of R and a negation of P. The negation of R will be false, true, false, true, false, true, false, true. And the negation of P will be 4 falses and 4 trues. And then we need negation of R implies the negation of P. We know this is a broken promise when this is true and this is false. So it's false here, it's false here, and it looks like it's true everywhere else. And then we need finally to do this entire statement. So what I really should do is copy this statement right here. But it won't fit, so I'm just going to put an arrow like that, and I think we can understand. So this is the left-hand side of the promise, and this is the right-hand side, and we're looking for true, false being false. That's the only way this thing can be false. Well, here's a true, but it's with a true. Here's a true, but it's with a true. Here's a true, but it's with a true. So there is no place where this is true and this is false. That means these are all true, which I guess I don't even need to write in, but I will. Which means that this is a tautology. It's all true, which means that this argument is valid. So problem 43 can be a lot of work. I first defined what my variables we're going to represent. P is the statement it is cold, Q is the statement the graduation is indoors, R is the statement the fireworks are postponed, and then I translate their words into a symbolic argument. So if P is true, then Q is true. If Q is true, then R is true. Those are the givens, those are the premises, those are the assumptions that we assume are true. And based on the truth of those assumptions, does it necessarily follow that P implies R if P and then R? Now we could make a truth table, and the truth table would be the truth table for this compound statement. If this premise is true and this premise is true, then both together they imply that this resulting conclusion is true. And if this statement had all truths, it would be valid. And I could do that. I did it on the previous problem. It takes quite a bit of work. But I told you there was another way to do it, and I recommended not doing it, but let me show you how it works. This particular piece of logic, I happen to have memorized, not because I work with this type of logic, every day of my life. I just remember that if P then Q, if Q then R, together that kind of makes a chain that connects P to R. So I remember that that's true. On page 140, it's called the law of syllogism, and it is right there, and it's a valid argument. And so if you were to remember that and be able to quote it, you could say that the law of syllogism proves that this is valid. Otherwise, you're stuck making a truth table. Now, I hope you did make the truth table, but see what you can do when you have those memorized. You can just call it valid because you've compared it to something you know is true. So I defined my statements P, Q, and R. P, it is snowing. Q, I am going skiing. R, I will wear a coat. Then I translated their words into a symbolic form of an argument. Being a little bit lazy, I wanted that symbolic form to be on page 140, but it wasn't. So to decide the truth of this, I either have to use a truth table or if I have to use some higher powered logic. All we know at this time is the idea of a truth table, so I've set up the truth table for P, Q, and R, and then I'm going to create the argument that we're going to try to prove. And so P and Q is one of the two assumptions or premises, and Q implies R. Q implies R is the second one, and together that implies the conclusion. So this is what we have to show the truth of, so let's get started. We need a P and a Q. And the only way an AND can be true is if both parts are true. So the rest of these are going to be false. And then we need a Q implies R. And we know that this will be false when Q is true and R is false, and that happens here, and it happens here, and that's the only times it happens. And then we need an AND statement on these two. Probably should have used a little more room there. I apologize, but I didn't. So there we go. So we're doing an AND, and the only way an AND can be true is if both parts are true. And so then we need a P implies R. And the only way that can be false is if this is true and this is false. So we have P here and R here, and we're looking for true false. We've got one of them there, we've got one of them there, and that's it. And now we have this, and we have this, and we need to do an implied right here. Again, I'm just going to do this because this whole statement has to be written right there, and why not? We're looking for this to be true and this to be false, then it'll be a broken promise and false. But there's only one true, and it's not matched with a false, it's matched with a true. The rest of these are false, and so what that means is that these are all true. That means it's a tautology. That means this argument, that means that this is always true, that means that this argument is a valid argument. It holds water logically.